Okay, this is an example that this was a bunch of data that was given to me, and I'm trying to design a test for this well. And these were some flowing pressures and rates that they did, I think, for the state. So this is a recreation of the tests off the completion reports. And what we've got here is they open the well up to flow for some number of hours, and it flowed at a constant rate of about 1.5 million a day. They shut it in for some number of hours, looks like 20 hours. So it looks like probably maybe a 4-hour flow, 20-hour shut in, 4-hour flow. And you can see that the rates they reported were essentially the same all the way across.
A 5-point test?
What's that?
That's what they call a 5-point test?
Yes. All right. So let's move on. All right. So what I did, and the reason I'm looking at this is I need to calculate the permeability in the reservoir in order to determine how long it's going to take me to get that gas out of the well. That's a function of permeability, and how long it's going to need to be shut in, because at this point we didn't have surface gauges, so I wanted to make sure that we didn't leave it shut in any longer than we needed to. So when I go back and model it, what you see here is my model is the red lines, and this is the permeability I used was too high. What this says is that in order to flow the 1.5 million a day that they flowed, with the high perm I only had to draw it down to 900 pounds instead of the 300 pounds that it took before. And so you can see in each one of these that the model didn't require as much drawdown as it did in actuality. All right, we look at a low perm fit. Here you can see that the model is saying, well, we got to take it all the way down to 0 in order to get the 1.5 million a day. And as it goes down, it's got to be drawn down even further. So when you're modeling these things, you have to look at these flowing pressures to make sure that they make sense. So here's the good fit, and you can see here that I've got a great fit down through each one of these flow periods. Even though it's requiring more drawdown as the test goes on, I've got a great fit throughout. My delta between the actual data and the model is essentially 0. So at this point, I've got a good fit for my design purposes. So for this test design, in order to prove up the amount of gas we were interested in, we were going to open the thing up. The initial pressure was 1,300 psi. We're going to open up and flow it for, what looks like 45 hours or so, and then shut it in. All right. They were looking for about a 7 psi drop in pressure from the 1,300 to the 1283. That's what that determines to be the minimum, that 5% error. That's the minimum drop I have to have in order to really believe the gauge. Let's see. My original design called for a flow of 36 hours, but logistics, getting people out to the well, made me flow it for 48. We had a 92-hour shut-in on this. So, like I say, this test, so when I call Paul, I say, Paul, this is what we're going to do. We're going to flow it at, 1.5 million a day or whatever for this period of time, and then we're going to shut it in, and we're going to leave it shut in for, in this case, what looked like 96 hours total, 140 hours from the beginning. So if we move on. Okay, with a short flow time, what happens is we only see here again, this is a shorter flow time than on the one I just showed you. The pressure only drops from 1,300 to 1,296. So it's only about a 4 psi drop in pressure. There again, that's not within the accuracy of the gauge. So we don't know if we're really at 1,296 or if we're at 1,298 or if we're at 1,295. We just don't know. We didn't take it down long enough. On that test where we also have a short shut-in, what happens is you see we're in radial flow, but there's no fall off at the end here. So there's no boundaries apparent in this test. If, on the other hand, we leave it shut in long enough, what happens is the pressure finally quits building, and you see this fall off in the derivative. That's why you need to design the test, because ideally you want to flow it, you want to leave it shut in until you see this point right here. And if you don't know what your permeability is, you haven't designed the test, for all you know, you might be cutting the thing off in here, and you have no idea what happens in the future. So here we are with an optimized deal. We've got our 7 psi drop from up here, and we've got a good long derivative on it. Okay, so here, that was the design. Here's the actual test. The actual test, we were not able to sustain the flow rate during that entire flow period. In fact, the flow rate dropped, but the pressure increased. So that's a normal trend in that you've got dropping pressure, dropping rate and increasing pressure. We're showing a lot of liquid loading in. That's what all this stuff is. We've got a few abnormalities in the curve through here, but we wound up at a 1257 as our last shut-in pressure. All right. When we look at the derivative, we see a whole bunch of scatter. And looking at the PPD curve that we discussed, anytime we have these inflections, that means it's not reservoir data. So essentially, everything from this point here to this point here is non-reservoir data and needs to be, this whole mess of jumbled here is not the reservoir talking. That's something else. Like I said, we saw a lot of liquid loading. We know that we had liquid and gas during this test. So this stuff is ignored. Here again, this part looks good. That's not a horizontal line, therefore Horner doesn't work. So we have to go to a different model. Just by coincidence, that looks like the composite model, again, where you have one set of reservoir conditions near the wellbore, a different set away from the wellbore, winds up with a pretty good fit. Going down through here, this is the bad data, but it kind of goes, bisects that bad data, and it's good back all the way over here. When we look at when we superimpose the model results onto the actual data, we've got a real good fit here. We're less than 0.1% difference up to a maximum of about 0.2% difference. But there again, that's not valid data, so I don't really care about that. This is actually wound up defining about a 72-acre reservoir in here. And ideally, I would have liked to have had a better fit back through here. I don't really know why I didn't at this point. It's kind of an old slide.
This is a production test, so this isn't a drill stem test.
This is not a drill. We're still in the pseudo-steady state depletion test. So, like I say, we've proven up in this case actually 326 million in reserves by the time it was all said and done. Production forecast on 72 acres of drainage. Here we can see this is a little bit better reservoir than that last one we looked at. This is the effective compression. There again, the high was 500 pounds of flowing back pressure. The low was 100 pounds of back pressure. So at 500 pounds of back pressure, you're going to get 320 MCF a day. You add some compression, maybe you can get that up to what would you call that, 3.8 or so. But that is going to tell you what size pipe you need, what sort of production forecast to expect. And again, with gas, I could actually extrapolate this out for several years, and I think it would probably be valid. Okay, this brings us, we've already talked about DSTs. First, we talked about the pseudo-steady state or depletion analysis, which is the second type of well test. The rate transient analysis is the third. As I just briefly touched on, the only input required are your reservoir parameters, your porosity, water saturation, initial pressure, and then you input the flowing rate and the corresponding pressures at that rate. No shut-in is required. Allows for determination of reserves even when there's no decline in producing rate.